In this video, we're going to look at and study what's known as improper integrals. There are two types of improper integrals. The first type is known as an infinite improper integral. Right, so this is one in which the limits of integration, the interval of integration itself, is infinite. And so, first, let f of x be a continuous function over the interval a to infinity. Then the integral a to infinity of f of x dx is equal to the limit as b approaches infinity of the integral a to b of f of x dx, provided this limit exists. We can also have f of x be a continuous function over the interval negative infinity to b. Then the integral from minus infinity to b of f of x dx is equal to the limit as a approaches negative infinity of the integral a to b of f of x dx. Again, provided the limit exists. In either case, if the limit exists, we say that the integral converges. If the limit does not exist, we say the integral diverges. So what we wish to do is we will determine whether the area of the region under the graph f of x equals 1 over x over the interval 1 to infinity is finite or infinite. Right, now remember that area under curve is simply an integral, so what we're looking at is we want to evaluate this integral. Well, this is clearly an improper integral, so we say this is the limit as b approaches infinity of the integral 1 to b 1 over x dx. So this is going to be limit as b approaches infinity, natural log of the absolute value of x as x goes from 1 to b, limit as b goes to infinity, natural log of b, we can drop the absolute values because clearly b is going to be positive, minus natural log of 1. Now the natural log of 1, of course, is simply 0. So we're left with the limit as b approaches infinity, natural log of b, and this is infinite. So we can conclude that the area is infinite, right? Because this improper integral diverges to infinity. Next, let's go ahead and evaluate the integral from minus infinity to infinity of dx over x squared plus 1. Now we can write this as the integral from negative infinity to 0 of dx over x squared plus 1 plus the integral from 0 to positive infinity of dx over x squared plus 1. Right, so we tackle each of these. So first, let's take a look at minus infinity to 0. This is going to be the limit as a approaches negative infinity of the integral a to 0 of dx over x squared plus 1. Right, well, that antiderivative is the inverse tangent of x. So it's the limit as a approaches negative infinity of the inverse tangent of x as x goes from a to 0. Inverse tangent of 0 is 0. So we really have now negative limit as a approaches minus infinity of the inverse tangent of a. All right? Now, that limit is clearly negative pi over 2. Right. So we get that this evaluates to positive pi over 2. To see why it's negative pi over 2. Right, consider the graph of tangent from, let's say, negative pi over 2 to pi over 2, right? Well, that graph is going to look something like this. Right? Both of these, negative pi over 2 and pi over 2, are vertical asymptotes. Right, so the question of this limit is essentially, what angle does tangent approach negative infinity at? And that would be negative pi over 2. See that? So next, we want to look at the integral from 0 to infinity of dx over x squared plus 1. Now we get the limit as b approaches infinity of the integral 0 to b of dx over x squared plus 1. Right? Well, that's going to give us the inverse tangent of x. Now x goes 0 to b. Okay, so we get inverse tangent of b minus the inverse tangent of 0. And again, inverse tangent of 0 is 0. So we're left with the limit as b approaches infinity of inverse tangent of b, and that is pi over 2. We therefore conclude that the integral from minus infinity to infinity of dx over x squared plus 2 is equal to pi over 2 plus pi over 2, which is just simply pi. Let's now go ahead and evaluate integral from 0 to infinity of x e to the negative x dx, right? Now this is clearly an integration by parts. So we use the substitution, let u be x, meaning that dv is e to the minus x dx. Right, du would just be dx, and v would be negative e to the negative x. Right, so then this integral be uv, so first let's rewrite this. Limit, b goes to infinity. Then this will be the limit as b approaches infinity of negative x e to the negative x. That is evaluated 0 to b minus the integral from 0 to b of v du. So e to the negative x dx, right? That negative cancels with the other negative, so that's why it's plus. So we're going to get limit as b approaches infinity of negative b e to the minus b plus 0, right? When x is 0, that whole thing goes to 0. Minus now e to the minus x evaluated as x goes from 0 to b. This winds up being limit as b approaches infinity of, let's write it this way now, negative b over e to the b minus e to the minus b, right, which is, again, 1 over e to the b, then plus e to the 0, which is 1. Clearly, this limit here is 0. If we take a look at this limit, factor out that negative. Using L'Hopital's rule, we can say that's 1 over e to the b, and that limit is also 0. So then that limit goes to 0. We're left with just the limit of 1, which is 1. So this integral converges to 1. Let's now look at what's called the p integral. Specifically, we want to be over a to infinity. For a greater than 0, the p integral from a to infinity, so integral from a to infinity, dx over x to the p, converges to a to the 1 minus p over p minus 1 if p is greater than 1, and it diverges if p is less than or equal to 1. So to see this, first, we're going to use the denotation j is equal to the integral from a to infinity of dx over x to the p. All right. Then this is going to equal limit as b approaches infinity of the integral a to b dx over x to the p okay. Now, if p is -1, then j would be the limit as b approaches infinity of the natural log absolute value of x as x goes from a to b, which gives us the limit as b approaches infinity log of b minus log absolute value of a. And as we know, this limit here is infinite. So this is going to equal infinity. I'm sorry. I didn't want p to be -1. That was p is equal to 1. I forgot it's in the denominator, right? So if p is 1, right, then we have all this. Now, if p is not equal to 1, we have two cases. First, let's look at if p is greater than 1. J is going to equal the limit as b approaches infinity of x to the 1 minus p all over 1 minus p. All right, as x goes from a to b, which will be the limit as b approaches infinity of b to the 1 minus p over 1 minus p minus a to the 1 minus p over 1 minus p. Right? But p is greater than 1, right? Since p is larger than 1, we can conclude that 1 minus p is less than 0. This means that the limit as b approaches infinity of b to the 1 minus p over 1 minus p is the same as writing this. Right? 1 over b to the p minus 1. Right, where now p minus 1 is larger than 0. Meaning that this limit is 0. So we can therefore conclude that j is negative a to the 1 minus p over 1 minus p, which is equal to a to the 1 minus p over p minus 1. If p is less than 1, j is still going to be the limit as b approaches infinity of b to the 1 minus p over 1 minus p minus a to the 1 minus p over 1 minus p. However, this time we have p being less than 1, which means that 1 minus p is larger than 0, which means this limit is infinite. Which of course means that j diverges. And so we've considered all three cases. If p is 1, it diverges. If p is less than 1, it diverges. So whenever p is less than or equal to 1, it diverges. And whenever p is greater than 1, it converges, specifically to a to the 1 minus p over p minus 1. And so that completes our proof. We next take a look at the next type of improper integral, the one where the integrand is discontinuous over the interval of integration. Let f of x be continuous over this interval. Then the integral from a to b of f of x dx is going to equal the limit as r approaches b from the left of the integral a to r of f of x dx, again, provided this limit exists. Second, let f of x be continuous over this interval. Then the integral from a to b of f of x dx is equal to the limit as r approaches a from the right of the integral r to b of f of x dx, once again, provided that this limit actually exists. Right, same as with the previous definition. If the limit exists, in either case, we say that the integral converges. If the limit does not exist, we say that the integral diverges. Right, well, let's take a look at the integral from 0 to 4 dx over the square root of 4 minus x. Now we look and we go, okay, well, clearly there's a discontinuity at 4, right? Because we'd have 1 over 0. So this is going to be the limit as b approaches 4 from the left of the integral from 0 to b dx over square root 4 minus x. This will be negative 2 root 4 minus x, evaluated x equals 0 to b. We'll get negative 2 square root of 4 minus b plus 2 times root 4, which is 2 times 2, which is 4. Now, as b approaches 4 from the left, that first term goes to 0, so we're left with 4. So this integral converges to 4. Now let's look at the integral from minus 1 to 1 dx over x cubed. This has a discontinuity at 0. So let's write this as the integral from negative 1 to 0 dx over x cubed plus the integral from 0 to 1 of dx over x cubed. Again, we want to look at each one individually. So let's start with the integral from minus 1 to 0. This is going to be the limit as b approaches 0 from the left of the integral negative 1 to b dx over x cubed. Okay. We're going to get negative 1 over 2x squared. X goes from minus 1 to b. Right. Limit as b approaches 0 from the left, negative 1 over 2b squared plus a half. Well, that is going to be negative infinity. We don't even need to evaluate the other integral, right? In order for our integral, sorry about the keyboard, in order for our integral here to converge, both of these pieces have to converge. Since this piece didn't, we can conclude immediately that our integral diverges. Now let's look at the integral from 0 to 2 of x times log of x dx. Right. Well, this has a discontinuity at 0. And so we're going to say that this is equal to the limit as a approaches 0 from the right of the integral a to 2 x log of x dx. Now this is an integration by parts. So we say let u be the log of x, which means that dv is x dx. du would then be dx over x. And v would be x squared over 2. And we're going to have x squared over 2 log of x evaluated as x goes from a to 2. Minus the integral from a to 2 of x cubed over 2 dx. Right? If we go and take a look at this, we're going to get 2 log of 2 minus a squared over 2 times log of a. Then minus x to the fourth over 8 as x goes from a to 2. I'm sorry. V du, this should have just been x over 2, which makes this term here x squared over 4. So we're going to go limit as a approaches 0 from the right of 2 log 2 minus a squared over 2 log of a minus 1 plus a squared over 4. Okay. Split this up. Okay. Clearly that limit goes to 0. All right, then we have, of course, these two limits. And that one will go to log of 4. That one just goes to 1. So the only question now is, what does this limit do? Well, we're going to have to do L'Hopital. All right, rewrite that as log of a over 2a to the minus 2. By L'Hopital's rule, we're going to get limit of 1 over a over negative 4a to the minus 3, which equals limit as a approaches 0 from the right of 1 over negative 4 a to the minus 4. No. A to the minus 2, right? I'm just going to do it this way then. Bring the a to the minus 3 up. That's a cubed. That 1 over a comes down like that. Yes, so we get a squared in the numerator. So this is negative limit as a approaches 0 from the right of a squared over 4, which is 0. So that means this limit is 0. And we get log of 4 minus 1. So this integral converges to log 4 minus 1. Let's look now at the p integral again. But this time, over 0 to a. So for a larger than 0, the integral from 0 to a of dx over x to the p converges to a to the 1 minus p over p minus 1 if p is less than 1, and it diverges if p is greater than or equal to 1. Now, this proof is very similar to the proof we did earlier, and so that will be left as an exercise for the viewer to do. Now, consider two functions, call them f of x and g of x, such that 0 is less than or equal to f of x, which is less than or equal to g of x, for all x greater than or equal to a. What we can do is consider integrals of these functions over intervals of the form a to t, right? So we're going to consider intervals of the form a to t. Clearly, we have 0 is less than or equal to the integral from a to t of f of x dx, which would be less than or equal to the integral from a to t of g of x dx for all t greater than or equal to a, right? If the integral from a to infinity of f of x dx, which is equal to the limit as t approaches infinity of the integral from a to t of f of x dx, is infinite. So this is infinity. Then the integral from a to infinity of g of x, which is also the limit as t approaches infinity of the integral from a to t of g of x, must also be infinity. If, instead, the integral from a to infinity of g of x dx, which remember is the limit as t approaches infinity of the integral a to t, g of x dx, is equal to L for some real number L, then the integral from a to infinity f of x dx, which is equal to the limit as t approaches infinity of the integral from a to t of f of x dx, is going to equal m for some real number m such that m is less than or equal to L. Right? This gives us what's called the comparison theorem. I'm going to say for integrals. Right? What this says, if f of x and g of x are continuous over the interval a to infinity, such that 0 is less than or equal to f of x less than or equal to g of x, then 1, if the integral from a to infinity of f of x dx equals infinity, then the integral from a to infinity of g of x dx is equal to infinity. 2, if the integral from a to infinity of g of x dx equals L, where L is a real number, then the integral from a to infinity of f of x dx equals m, where m is a real number, such that m is less than or equal to L. Right? This is useful if we don't really care about the value of an integral. We only care whether it converges or diverges. Right? So this theorem will come back into play a little bit later when we start studying infinite series.